In this chapter, we are going to talk about chemical equations and different types of calculations that you can do with them. This is really helpful if you are interested in setting up a chemical reaction. You want to know how much you're going to produce, or if you have a certain amount of a thing that you want to make. It's helpful to know how much you need to start with. And so that kind of idea of figuring out how much you need or how much you're going to make in chemical reactions a lot of times is referred to as stoichiometry. And so that's why the joke, what is the chemist's favorite plant? It's a stoichiometry is on this slide. All right. Well, let's jump right in. So to understand that, we really need to understand chemical reactions and chemical equations. And chemical equations just describe proportions of reactants and products during a chemical reaction. Now, one of the things you can do if you're looking at a chemical reaction to orient yourself is to find the arrow. The arrow is right here, and that is going to separate the reactants from the products. Now, the reactants are just the substances. Yep, there we go. Substances that are consumed during the chemical reaction. And then products are the substances that are formed during chemical reactions. Right? When we look at chemical reactions, there's a few things to be aware of. The identity of the products and reactants are specified in these reactions by their location. If you were to write this reaction from the words that are written here, it would be sulfur trioxide, SO3, plus water, right, goes to sulfuric acid. I want to remind you that you need to use the upper and lowercase letters that are on the periodic table because CO and CO are different. One is cobalt and one is carbon monoxide. So make sure you're aware of that. Now, other things that you're going to see when we look at balanced reactions are these letters next to the different chemical substances. Those tell us the physical state of the products and reactants. So S is solid, L is liquid, and generally that's shown as a cursive L. G is gas, and AQ is aqueous, which just means mixed with water. Sometimes you can run into other things in chemical reactions around the arrow. So if you see a delta over an arrow, that means heat, right? Sometimes you will see some kind of like reagents, like catalysts, over the arrow. Other times you will see temperatures, like maybe it says 180 degrees Celsius, and that just gives us some information about the reaction conditions. Now, when we read a chemical reaction, right, sulfur trioxide reacts with water to form sulfuric acid. There's some context clues that are going to clue you in. That's where the arrow goes. To form is one. Produces is another. And I'll point those out as we see them in problems. Now, when we look at this, we can look at this and say one molecule of sulfur trioxide reacts with one molecule of water to form 1 molecule of H2SO4. We can also, and we're going to talk more about the mole in the next screencast, describe this by saying 1 mole of sulfur trioxide reacts with 1 mole of water, which reacts with to produce 1 mole of sulfuric acid. This second equation here, I want to point out a few things. One of the things I want to point out is there are numbers in front of sulfuric acid and water here. So we have iron oxide reacting with sulfuric acid to form water and iron sulfate. These are called coefficients. And so the way we would read that is we would say 1 molecule of iron oxide reacts with 3 molecules of sulfuric acid to form 3 molecules of water and 1 molecule of iron sulfate. And so those coefficients are what we're going to use and change in balanced reactions. So balanced chemical reactions follow the law of conservation of mass. When we look at this reaction here, we have CH4 reacting with ammonia, which is NH3, to form HCN and H2, or hydrogen gas. Again, these are the reactants and these are the products. And what we see here is with no coefficients, this side has a lot more hydrogen. Hydrogen are the white spheres here. Than this side. There's 7 hydrogens here, but only 3 here. Now, the number of nitrogens are the same, and the number of nitrogens here are the same, and the number of carbons here are the same, but we have a problem because this does not obey the law of conservation of mass. It's not balanced. So we need to go about balancing it. There's a 4-step method to balancing chemical reactions. You need to write the correct formulas for the reactants and the products. So I'm going to do the one for before, including the physical states. Okay, if the states are given, okay, so you include the physical states if given, and then you check whether the expression's balanced by counting the atoms on each side of the reaction. Now, when I do this, I like to line them up. So I say, okay, there's 1 carbon here, and then I write carbon again and say, look, there's 1 carbon there. And then there's 1 nitrogen here and 1 nitrogen there. And then I'm going to count my hydrogens, and there are 7 hydrogens there, and then there are just 3 hydrogens there. And then balance, so there's a few kind of like tricks, okay? And it's in what these rules say is balance an element that appears in only 1 reactant and product first. So, for example, hydrogen appears in both the reactants and like both reactants here. It appears in both products here. I don't really want to start with that if I can balance something else. Other hints, which I'm going to kind of put here in 3, is if you can, leave hydrogen and oxygen last. A lot of times, if you can balance everything else, those will just fall out and become balanced. Also, leave individual. There we go. Individual elements to last as well. So like the H2 I'm going to leave to last. Other kind of hints is that if you have polyatomics that don't change between the reactants and products, balance those whole. And I'll show you, I'm going to show you examples of all these. I just wanted us to get it down. So when I talk through it, you know what I'm talking about. All right. So here we go. When I set to balance this, I see that the carbons are balanced here and the nitrogens are here. I start because those are only in one molecule here. So now I'm left with my hydrogens. There are 7 hydrogens here and there are 3 here. There is 1 here and 2 here. This guy is all by himself, okay? Because he is all by himself, you can come here and put the coefficient here, which is 3. And then it's 3 times 2 gives us that there's 6 hydrogens plus 1. And now we have 7 hydrogens. And so this is now balanced, okay? And you can always, I love this because you can always go back and double check. You know, you can always count. Let's do another one. And I'm going to omit the states just for brevity so we can focus on balancing. I want to remind you that there are some elements that are diatomic. We're going to talk, I've got a slide that shows those in just a second, but that's why we have N2 and H2. Okay, so we have N2 plus H2 forms ammonia, right? And when we look at this, we're going to start with just listing what we have. So we have 2 nitrogen atoms, and we have 1 nitrogen here. And then for hydrogen, we have 2 hydrogen atoms, and over here, we have 3 hydrogen atoms. So when I look at this, I say, all right, these 2 guys, they're individual, they're by themselves. I'm not going to start there. I'm going to come over here and I'm going to balance the nitrogen first. I want to save the hydrogen till last. So I'm going to start by just putting a 2 here and see where that leads me. When I do that, this changes to a 2 because the 2 coefficient here is distributed where now there's 2 nitrogens here and then 2 times 3, that gives us 6 hydrogens here. Okay, so now my nitrogens are balanced. I don't have to do anything else there, but I need to take care of my hydrogens. So I come over here and I say, okay, how can I go from 6 hydrogens, from 2 hydrogens to 6 hydrogens? And the way I can do that is put a 3 here. And 3 times 2 is 6, and that gives me 6 hydrogens there. Let's do one with some polyatomic ions. So when we look at polyatomic ions, so we've got ammonia sulfate plus lead nitrate. If it broke up there, I had an issue on my side with the screencasting, so I apologize. So we've got ammonia sulfate reacts with lead nitrate to form ammonia nitrate and lead sulfate. And so what I'm going to do here is I'm going to look and I'm going to say, okay, I've got a polyatomic ion here and a polyatomic ion here, and they don't change. They're the same thing. And so I'm going to say, all right, I'm going to balance those whole. So NH4, there's 1 of them. Nope, there are 2 of them on that side. And then NH4 here, there are 2 on this side. And then sulfate doesn't change. So SO4, there's 1 here. And SO4, there is 1 here. Then lead, there's 1 lead. Lead on this side, there is 1. And then nitrate doesn't change, so NO3, there are 2 of those. And then NO3 here, there are 2 of those. No, there is 1 of those. Ooh. Okay, there is 1 of those there. So when I look at this and compare here and here, I can already see a mistake I made. right here. There's just one of those. One. There we go. When I look at this, I see that I have 2 ammonias here, right, and 2 nitrates, and just 1 here and here. I can put a coefficient 2 here. When I do, that changes the entire ammonia nitrate, the triammonia to 2, and the nitrate to 2, and now it's balanced. That is a lot easier than breaking those up if you don't have to. Sometimes you do, and we're going to see an example where you can't use that method, but that's really helpful. I want to remind you when we go through this that there are 7 diatomic elements. So if you see a description of a chemical reaction where there are words and you have to go from words to the chemical formula and they refer to nitrogen, it's going to be N2. Or if they refer to iodine, it's going to be I2. So you really need to remember these. Again, there's 7 of them, and I know hydrogen's like over here by himself, but these form a 7 on the periodic table. And so it helps us really remember these. I would mark these off on your periodic table. So I want us to do another example type, and this is where we have words, and we're going to go from words to the balanced equation. And so here we are. It says nitric acid reacts with calcium hydroxide to produce water and calcium nitrate. Now this builds off of what we did in the previous chapter where we were naming ionic and covalent compounds as well as acids. So we remember that nitric acid, that acids have an H out front, right? And if it's nitric, it is based on the nitrate ion, which is NO3, okay? And we're going to ignore states just for some clarity here. Then it reacts with calcium hydride, so that with tells us it's still, and reacts with tells us it's a reactant. So to figure out calcium hydroxide, we remember and look at our periodic table that it's calcium 2+. And we've memorized our polyatomic ions and know that's OH minus. So we're going to come here and we're going to crisscross these guys down. And that's going to give us calcium hydroxide. And remember, we use a parentheses there because there's more than one polyatomic ion. Okay. Then this goes to produce water. Now water's H2O. And calcium nitrate. So again, calcium is 2+, and nitrate is NO3 minus. We crisscross these down, and we get CaNO3 2. All right, let's now figure out and keep track of all of our elements. When we look at this, we see that the polyatomic ion nitrate stays the same. It's NO3 in the reactants and NO3 in the products. So we come here and say, great, we've got NO3 here, there's just one of them. And then we've got NO3 here, and there's 2 of them, okay? I'm going to save hydrogen till the end because it's a little bit everywhere. Because notice here that there's OH here, but there's no OH over here. This means you really need to break these apart and balance them as oxygen and hydrogen. So let's look at calcium. There's 1 calcium here, and there's a calcium here. There's 1. And then for hydrogen, there are 3 hydrogens. And then for oxygen, there are 5 oxygens here. So when we look, we see there are 3 here and then 2 here. So we add those together. We come over here to look at hydrogen. There are 2 hydrogens, and then when we look at oxygen, there's 3 times 2, that's 6, plus 1, that's 7. There are 7 here. Now, I look at this and I'm going to save hydrogen and oxygen to last. And instead, I'm going to balance the nitrate. And so when I come over to balance the nitrate, I'm going to put a 2 here. And then I am going to recalculate this side. So when I put the 2 here, that makes that 2. And then it also changes my number of hydrogens to 4. And it changes my number of oxygens to, so there's 6 oxygens here and 2 oxygens there to 8. Okay. And so when I come over here, right, my calcium and my nitrate are balanced, and I'm left with hydrogen and oxygen. I'm going to look at water for a second and just try it with 2 waters because, and I want to do that in a different color so that you can see it. So let's do it in purple. 2 waters. So when we look at this and calculate, now we have 4 hydrogens and 6, 7, 8, 8 oxygens, and we're balanced. Okay. So sometimes there's a little bit of like trial and error there. But you can always double check, recount, make sure that the number of atoms on both sides are the same. Let's do another one. If I broke up there, it's because I accidentally paused it. All right, so let's do another one. Sulfur, present as an impurity in coal, is burned in oxygen to produce sulfur dioxide. Now here's the deal. It says it's burned in oxygen. That's a diatomic molecule. That has to be on your radar. That's so tricky. You've got to watch for it to produce sulfur dioxide, and that's SO2. And when we look at this, this is balanced, right? There's 1 sulfur on each side and 2 oxygens on each side. So sometimes these are going to be given to you and they'll already be balanced, but you definitely want to watch out for those diatomic molecules. We're going to do more examples in class, and as always, feel free to pop by my office if you have any questions.